All right, folks, let's go ahead and get started. We do have a long session today. My name is Len Thompson. I'm Broadcom's Mainframe Division Community Manager, and I want to welcome you to today's webcast. Before I hand you off to our speaker, a couple of things to quickly go over. First, if you have questions or feedback along the way, and we always hope that you do, please do use the questions box right under the GoToWebinar control panel to ask them. We'll get through as many of those questions as we can today. If for some reason we can't get through all of them, I'll make sure that the team gets everything they need to follow up with you later. Secondly, we are recording today's session, and the replay will be available out in the mainframe software community sometime tomorrow. And the last thing for me is that we are always trying to make sure these sessions are as valuable as possible. So with that in mind, I pulled together a quick survey that will appear at the end of the webcast. That's it for me. So take it away, Andra. We cannot hear you if you are talking.
Before we start, I should probably say a few words about myself. So I have a system and application administration background, and I was a developer, both in OOP and procedural languages and frameworks. And then some 10 years ago, I switched to QA. That is quite counterintuitive for most people, even as I watch other webcasts, because many developers somehow see QA as something with less expertise and less fun development. But I did that because I got an opportunity to play with exotic system and very exotic indeed. It was security system, namely ACF2 on IBM mainframes. And since I came from development, I started with test automation from day one because like no way I was going to do manual testing. But I found out the bad way that automation does not equals quality, because even though I built very nice automation, it didn't catch the defects it should have because there is no correlation between automation and test coverage. And ever since I got switched to a different product on databases, which was not so fun, I hence tried to improve the quality itself. I had the good luck of being gifted with ISTQB training, and from that I could spring my feet and try to go through QA standards. And when I ran out of standards to read and things to improve from them, I went to seek inspiration in the aerospace industry software quality assurance, because aerospace is the area where most lives are at stake. If your software crashes on an airplane or rocket, everyone just dies. So they have the best stuff there is. And I managed to cherry pick the things which I think are valuable from the aerospace software quality assurance to even corporate software. And we successfully applied that here at Broadcom. So as I said, I have 10 years of QA experience under my hands and then some as developer. I am formerly a senior QA, and I would have been principal back in CA, but then came merger with Broadcom, and with its flatter structure, I remain senior one. And just to note for everyone, you are not seeing my face. That is not a technical problem. We are not streaming video. So enough of myself. Let's go to the topic. If you try to get your hands on testing, I really dislike the word because it's so general and it keeps getting people all sorts of wrong ideas. So let's try applying something called systems thinking, which means systematically decomposing a system to its logical components. If you take the most official definition of testing there could be, straight from the International Software Testers Qualification Board, it tells about something concerned with planning, preparation, and evaluation of software, blah, 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 blah. But you see, the problem here is that they already list 3 logically separate activities regarding testing. And that's just putting too many things into one bag. If we go to Merriam-Webster, that's slightly better. They say that testing is subjecting some subject of test to some conditions, and then using the results to verify if it's accepted behavior or not. But this still conflates 2 activities, subjecting a system to some activities and evaluating the results. So if we go down to ground zero, what testing literally and only means is subjecting a system to some activities and recording the system response. And now I can see you are probably confused because I lured you all on a webinar about aerospace QA, and instead you see something which looks pretty much like nitpicking. But it's quite important because testing is culminating act in the quality control workflow. And as such, it overshadows many things which are actually extremely important, yet are not so obvious. So to demonstrate why this is important, let's take flying to the moon example. For centuries, people wanted to fly to the moon, and everything there was written, for example, Jules Verne's The Path to the Moon, was concerned with the act of flying to the moon itself. It seemed simple, right? Just sit on some rocket or giant gun, shoot to the moon, and voila, you're there. But when we actually, as humanity, got to flying to the moon in the Apollo moon space program, we soon found out that it's not quite so simple. First, we had to be able to calculate the kind of rocket and path to the moon so that we would even hit it and not get lost in the endless universe. And we found out that we need a 200-ton rocket with some extreme engines to even lift off the ground and get to the Earth orbit. Then we had to design the rocket, and rocket scientists are not a synonym from some extremely difficult science or for nothing. Then we had to deal with the vacuum in space. That's something that pretty much everyone who was prior talking about flying to the moon grossly neglected. If Jules Verne had fly to the moon the way he described, he would have suffocated and or exploded in the vacuum of the space. So dealing with vacuum was something extremely important. Then, of course, was building the rocket and lunar lander, but even managing inventory. Again, an activity which is definitely not obvious, but which is indispensable. The databases as we know them today actually came to existence to manage the inventory for building the Saturn V rocket, because there were so many items needed to build the rocket that even the biggest teams of human clerks and accountants couldn't keep track of all the stuff. Hence, the IMS database engine was written, and then from now that on, the SQL came to existence. Then, of course, you cannot just fly to the moon, the most sophisticated rocket the humankind has ever built. We all know that training astronauts was extreme process. And only then, after you meet all of these prerequisite activities, you get to the actual flying to the moon. So as you can see, flying to the moon suddenly looks like not the only thing, not the most important thing, but almost one of the most simple things of all those previous. And yet, the culminating act is not the last step. From space, you still have to return to the Earth without burning in the atmosphere. And so, after testing itself, there is still one more thing to do. So, describing why it's important to decompose the system to its logical parts, let's get to testing. Testing is the climax of all the activities in quality assurance. More precisely, it would be said test execution. That is testing. Running some tests, subjecting the system to something which happens to it and recording the results. But how do you test? You execute some testing scenarios, either manually or via some automation. So these test scenarios are some instructions which had to come from somewhere. They didn't just magically materialize out of thin air. So someone had to implement these instructions. And that someone first has to design the tests so they can be implemented. And tests can only be designed if you do thorough technical test analysis, which means analyzing the system under test in all its contexts, finding all the things which can go wrong, and creating tests which will cover all these things which can go wrong. And of course, you cannot do that without understanding both the system under test and its context. So you can see that the testing, which everyone talks about, go tested, testing, web burner testers, that's just one little part in a huge workflow. And to top it, it's the least qualified part, because if we take testing as executing some instructions which someone else wrote, there is no skill to that, because if even a computer which has no intelligence, it just mechanically executes some instruction, can do it, it is a mindless task. The skill and human expertise is hidden in the previous phases, especially the technical test analysis and test design and implementation. And this is something which used to be understood years ago, but this knowledge has since vanished. Some 10, 15 years ago, the people who just executed the testing scripts written by someone else were called not testers, but test technicians. And the people who did the analysis were called technical test analysts. And the people who designed the tests and implemented them were called QC engineers. So if you don't only execute some test script written by someone entirely different, but if you also create the scripts, create the tests, and define them and design them, you are not a tester. You're actually a QC engineer. But wait, there is more to it, because even after you culminate all the design and analytical activities with actually executing the tests, there is still results to be evaluated. And executing the tests and evaluating the results are not the same things. Sometimes evaluating the correct results is actually more difficult than running the tests themselves. But here's the thing. If everyone focuses so much on testing as test execution, how much effort are they putting into the technical test analysis and test design? Because tests can only be as good as the analysis and design which created them. So if you never gave a conscious thought about technical test analysis or test design, if you just went to test, as managers like to say, how much effort did you put into the test analysis and design? Wasn't it just a subconscious process at the back of your mind while you were typing something into Visual Studio Code? And if it was a subconscious process, how much can you trust it to really cover all the stuff that's important, to analyze all the things which could go wrong, and to design the test so perfectly that they would really catch all these cases? And of course, there is one more problem. Since we live in 2020 and everybody is obsessed with the computing power which is suddenly at our disposal, there is huge temptation to tackle the mindless testing and avoid the analytics with just using computing power to somehow, go through this without thinking by procedural generated automated tests, or even better, by random tests. I have seen this in my own company. Some teams opted to do testing based on random data, and the managers completely loved this because the team said, yesterday we ran 3,000 random combinations. How awesome does that sound? Only until you come to employ mathematics and see that 3,000 combinations or even 3 million combinations are a grain of the sand on the ocean's beach, because you would need much, much more than that. There is an often used metric of code coverage. Imagine you have a very simple computer code with some branches which don't go into nested tree structure, but instead linearly follow each other. So you have some code, there is an if statement, something happens, something else, if statement, etc. Say that we wanted to create test cases which would achieve 100% code coverage. For such a code, we would actually only have to code 2 test cases. One test case would always go up in the path, while the other test case would always go down. Voila, 100% path code coverage. Managers are happy. So the number of tests you need to achieve code coverage is 2 times the number of branches. However, what if there was a defect hidden in the code, which would only get triggered if the path went like this, and then down, and then up again? None of the two tests, one of which always went up and the other one always down, could discover such defect. You would need to actually test all the combinations of all the paths there could be. And that would be something called path coverage. Combinatorically going through all the paths which are possible in the code, regardless of how complex or loopy, etc. And that's a different method entirely, because while code coverage can be achieved with just 2 times the number of branches in the code, path coverage is exponential. It requires 2 on the power of number of branches in the code. So to illustrate this graphically, if you had a very simple program with just 70 branches, that would require 1.2 sextillion test cases, which is about the number of grains of sand on the entire Earth. And if you somehow magically turned all these test cases into automated tests, and it took each test case 30 seconds to run and evaluate, which is very optimistic, it would take 10 on the 15 power of years to run all these tests, which is so huge number that no one can understand it. So for the reference, 10 on the 15th power of years it is approximately 6,000 times the age of our universe. And that's just the simple program with 70 branches. If you get to something as complex as the Solaris operating system, there are more paths in the Solaris operating system than there are atoms in the entire known universe. Let that sink in. More atoms than the whole universe. That's the number of tests you would need to achieve 100% path coverage. So as we can see, the mathematics prove that you can never achieve 100% path coverage of any even reasonably complex computer code. Which brings us to a concept called the testing house. If code coverage is reasonably achievable, but usually not enough, it's a floor, the bare minimum. If path coverage is theoretical maximum but impossible to achieve, it's the roof. And the question stands, how do we pick the important test cases from somewhere in between if code coverage is not enough and path coverage is impossible to achieve? And the answer is human brains. Because most of the test cases regarding path coverage, 99.99999%, would be useless. They would never trigger any defect. There would not be even a probability that there would be a defect. But a human analyst can, using his brain and knowledge of the system, pick just the right test cases which are probable to trigger defect if there is one. And these hand-picked test cases are the middle grounds, and the process which finds these test cases and identifies them is called technical test analysis. But wait, there is even more. A lot of testing organizations or managers or teams are obsessed with measuring code coverage and the percentage of automated tests. Nothing against these. It's nice to achieve 100% automated tests. We had reached 99.6% in my previous team. But unfortunately, these metrics are grossly misleading. So let me demonstrate graphically. Imagine we have such a very simple function. It divides two numbers. It returns the divisand if there is no zero in any of the inputs. And if there is a zero, it returns zero as well. We can write automation. So I just wrote a little test automation code, which we feed with triplets, where the first number is the thing which we will divide, the second number is the number with which we will divide, and the third number is the expected result. And as I have just described, it takes just 2 test cases to achieve 100% code coverage. So this test case goes through this path, and the second test case goes through this path. And because it's such a simple code, it also achieves 100% path coverage. And we have 100% automation. So everything is 100%. Are we happy? Are these 2 test cases enough to cover such a simple function? No way. Because these 2 test cases have just went through all the paths in the code, but they did nothing to check the code can handle various sorts of data. For example, this test, although it may cover the entire first path, did nothing to ensure what happens if we are actually putting some decimal number on the output. We are dividing whole numbers and expecting a whole number. We haven't tried anything regarding negative numbers. We haven't checked the boundary values of floating point numbers, from which this is minimum and this is maximum. And we haven't even tried dividing them, which should, in floating point numbers, result in positive infinity. We haven't checked what happens if the output has periodic development. Doesn't it overflow our function, our software? And finally, we haven't done anything to test the code in a system level. That means on the host operating system and on the hardware. For example, Pentium 1 processors had floating point division bug in the mathematical coprocessor. It just didn't compute correctly. So there is a test case to verify that we are calculating it correctly or compensating for it. So as you can see, even if we achieved 100% automation, 100% code coverage, and even 100% path coverage, the mythical beast, it would still absolutely not be enough. Because verifying the software is not only about code flows, but also about the data which flows through the code. And now to give you some rest, there are two questions. First, there is something wrong with the code, or maybe there is not. You can see that what it returns is 0 if you try to divide 0 with 0 or anything with 0. But the expected result is not a number. So is one correct and the other not? Are both correct? Is none correct? Does it matter on the context? You can write your answers, if you have any, into the questions box, and then we'll read them out.
No responses yet.
Okay. Anyone has any ideas? If you divide 0 with 0, what would be the correct result? I'm not talking about code, I'm talking about general world, general mathematics.
One person responded with 0, one with undefined, one with runtime exception.
And these are all correct because it depends on the context. In the IEEE 775 standard for floating point numbers in coding, the answer is that it can be 0. Others, for example, Java, I think, implement this as not a number, as invalid number. And it really depends on whom you ask. Because some mathematics will use limits to prove that it's infinity, others will prove that it's an invalid value. So the question is, what is the task of the code? What is the context where this function will be used? Because that is what determines what is the correct result. You cannot just pick any of those which are correct because multiple are correct, yet they are not the same. And there is one thing regarding automation. I often like to point it out because very few people notice it. So there is a problem with the automation script here. It's sanitized, so we try calling the function with the inputs, and if the function crashes, we catch that crash, type some error into the log, and then we set the result number to not a number. So there is something dangerous about this regarding to test evaluation. What could it be? Anyone has any ideas?
No responses yet.
Okay, so what if I tell you that if we divide 0 by 0, the expected result is not a number? So we can expect not a number as an expected result. And here we are setting not a number as a result, not when the function returns it, but if the function crashes. So what would, for example, happen if the function crashed each time? The first test would fail because it expects it expects 1 at the output, and it would get not a number. But if the function crashes with the second test case, what does it do? It expects not a number. Since the function crashes, it gets not a number. It evaluates if not a number equals not a number, and it does. So the function would claim to be passed, although it was in error. And this is something which happens extremely often with any sorts of automated tests. For example, when we were testing databases, often the favorite approach would be to have the tested code connect to database and do some operations with the data, and to verify the correctness of these results by writing a parallel test script, which would connect also to the same database, fetch the same data, do the same operations, and verify if those two results match. Now, what happens if the database is offline? The production code which is tested returns error message, cannot connect to database. And your test script, which is supposed to independently validate the result, returns the same, cannot connect to database. And if you compare the strings cannot compare to database and cannot compare to database, they are identical, and hence the test is called as passed, although actually it never even ran in the first place. This happens all the time in automation, and very few people actually care about it. Which brings me to another step. Every testing conference, every QA conference, and most QA organizations are obsessed with test automation. It's pretty much the only thing people talk about, people present about, and it's almost the only thing that managers usually demand. And yes, test automation is awesome. For some things, for some problems, it is the only solution, but it is not a cure-all medicine. It is just a tool, and that tool has pretty large limitations. And if you are not aware of these limitations, you will get burned. So the first thing is that, as we've already seen, test automation cannot replace test analysis, because it cannot cover defects with brute force randomized testing, because there would be 16 paths to test. But even if we did cover all the paths, it would still not be enough, because we have to test the data flowing through the code paths, not just the paths themselves. And test automation cannot generate brute force the testing data because of something called the infinite monkey probability mathematical problem. There is a theorem which says that if you had a monkey randomly typing on a keyboard, eventually in infinity, it would generate the whole work of Shakespeare. Yet in the real world, if you don't have infinity, which gets you away with anything, it's the exact opposite. Because the probability that the monkey will write Shakespeare's play decreases with each key press. Because we are not talking about independent letters. They have to be in sequence. And so the probability that you hit the first letter right is just 1 to the number of letters in the alphabet, 1 to 26. But the probability that you hit 2 subsequent letters right is 1 to 26 multiplied by 26. And that you hit 3 letters right, 1 to 26 by 26 by 26. Yet in software engineering, it's much worse, because you don't have just 26 letters of the alphabet. If you have some frame for input where a user can actually write, you have to expect at the very minimum 255 characters. So imagine you had a field where a user can type in 4 letters, and you wanted to replace analysis with some brute force test automation. So you would have your computer generate test case for all combinations of letters which can actually be there and cause some defect. 255 multiplied by 255 by 255 by 255. And do you know what is the result? 4 billion test cases. It's exponential again. So test automation can never replace analysis. The only thing which test automation can do is increase the efficiency of running tests. But if you remember the workflow we talked about at the beginning, that's just the test execution phase. So when you compare the manual testing and automated testing, the research and test analysis and test design phases are of equal length. You cannot solve anything there with test automation. Then the thing which takes most of the time in manual testing is the actual manual testing itself. And I know, because I was there. On the security product, we have a very low percentage of automated tests. So when we wanted to run the full regression of the entire product, it took a team of 5 people 2 months of intensive work. Of course, that was only possible because we had 2 years release cycles. With agile software development, with its short iterations, that's unachievable. So what happens if you instead go for automated tests? Well, it depends on how many times you actually execute these tests. Because if you only executed the tests once, you wouldn't get much time savings. Because what you have saved on actually running the tests, which can run as fast as the computing power you have at your disposal allows, you have to invest, you have to buy that time savings by a significant investment into actual test automation. So this only begins returning benefits if you run the tests multiple times. So test automation is pretty much necessary if you want to run frequent regression testing. And that's also its biggest advantage. And managers often think that it will allow them to trade many test technicians who just execute manual tests for fewer test automators who just implement the automated tests. That's not so true because the analysis workload remains the same. And since in most organizations there were not many test technicians, but instead multi-purpose quality control engineers who did everything from analysis through design to testing and automation, you don't save much people. But there is one more thing which is often neglected and it will burn you, and that is automated tests maintenance. We've been doing automated tests by default for every new feature for the past 7 years. And throughout the last 2 years, we actually started hitting some serious problems with maintenance of the older regression test case suites. Because whatever you use to automate, you are dependent on several external things which you cannot influence. You are dependent on the host operating system. If some APIs change there, or some libraries or something, or some procedure which you previously used, for example, for authentication or network access is dropped, you have to refactor all your tests to keep working. If you are dependent on some testing framework, you have to continuously maintain your entire automated test case suite to keep the pace with the changes. And if the old version of the test framework you are using is dropped entirely, well, good luck. So the number of test case suites which were completely automated, but we didn't have capacity to maintain them, and thus they were unusable, kept growing until we have to dedicate several sprints or even PIs to just fix the old automated tests. And the maintenance is the rainy cloud looming on the horizon whenever you start with automation. And anyone who thinks about automation seriously and wants to have like long time sustainable projects need to think about that in advance and possibly even allocate some capacity for automated test maintenance like to the future. And the last thing is that there is no one size fits all. I have several times seen a project where some manager decided which test automation framework will be used, only to find out that that particular test automation framework was very poor fit for the software to be tested. We are talking about backend software mostly here. And everything just had to be either thrown away or the tests written in that unfitting framework became like a dreaded unicorn. Nobody knew how to maintain them, just run them, and if any changes were supposed to be made, it took some serious overhead. So to reiterate, test automation is only one of the ways of executing tests, not creating them. It cannot design tests, it cannot pick sets of useful testing data, and it cannot discover risks. All these things have to be done by human analysts with brains, skills, and knowledge of the product and environment. Automation can only efficiently execute some predefined test scripts, but it's like with automated cars. If you have even the best automated car in the world, and you don't tell it where you want it to drive you, it cannot go there. It's just executing some orders. You have to give it those orders. So the point which I would like you all to remember very well is that automation is not quality assurance, test automation. Test automation is a specific type of software development where QA is just the customer. And too much focus on test automation, which we are seeing for the last, say, 5 years, has one effect. In the workflow of quality control, it shifts all the attention and resources away from analysis phase to the execution phase, and that harms quality. So if you want to have aerospace grade QA or even good QC, you have to return to the fundamentals and refocus on the technical test analysis. Test analysis has levels about which, for example, Boris Beiser talked in his famous 1990s book about testing and analysis. The first level is only positive tests. That means you are trying to prove that the software works as intended. That's nice, but from the nature of this kind of testing, you are de facto saying that you are guaranteeing that the software will work as long as all the users will be using the exact same clicking and working through the product as your testers, and as long as all the customers would be using your testing data and nothing else. If anyone deviates from your positive tests, anything can happen because nothing else was checked. So that's obviously insufficient. So the second level is destructive testing, which sounds evil, but it's actually not. It's just focused on not only proving positive tests, for each higher level also contains all the things from the previous levels, but it tries to find the weaknesses. What could break the code? And the intention here is to find the defects before the code is released to the customer. Because the earlier you find the defects, the cheaper it is to fix them, and the less harm there is to your reputation as a good vendor of software. And destructive testing also starts with one very important thing, and that is challenging developers' assumptions and discovering unsanitized inputs. Imagine you have a field where age of a person is supposed to be entered. So the developer is a smart guy. So the developer starts writing code and did some basic sanitization. So there is a check added in the code if the age is entered as too high number, so it doesn't overflow. There is also a check that the age must not be entered as a negative number, because if you are processing human age, negative numbers can cause all kinds of havoc. So that looks nice. The developer is happy. They didn't just ignore the function. They didn't ignore the input. They did pretty good sanitizations. So what is the assumption here that needs to be challenged? What about the type of the input? The developer was subconsciously assuming that the input will always be a number. What if a user, not a hacker, not a troll, just someone inexperienced with computer software, goes and writes 65 in capital letters, not a number, instead of string of characters? The developer never assumed any such thing can even happen. So obviously there are no sanitizations for that. So it is a role of destructive QC to challenge all these assumptions and try all these things. There is a category for this in QC, which is called human operator error test, which means you have to try anything that even the most insane user could try to enter into your inputs. But that's still quality control. Level 3 of test analysis would be reducing risk, not proving that the system works, not proving that the system has weaknesses which can be fixed, but instead trying to reduce risks. So you all, the entire development team, can trust the software. Level 3 is already system focused. It doesn't focus on the release. It doesn't focus on the inputs. It focuses on the entire system because your software doesn't exist in a vacuum. It runs on some host operating system, potentially host frameworks like .NET or Java. It runs on some host hardware, and all these things can influence the software you are about to test. So you need to test all these integrations and external influences to the extent they can influence it. And also, if you're talking about systems, on level 3, we start with reviewing the design. So QA engages not only in creating the tests, but trying to find the possible risks and engaging in design and re-architecture so that the possible risks are sanitized actually before they are coded in. And finally, we have the highest level of them all, level 4, which is preventive action across the entire system lifecycle. This is the aerospace level QA. From the others, which it also includes, it differs mostly by using systematic reliability engineering techniques with fault hazard analysis, and by using models which go through the system or data flows and try to predict what failures there could be by actually simulating. But the most visible part, which is most visible to the entire team instead of the analyst, is adopting feedback loops. The analysis designed feedback loops across the lifecycle. So we have levels, and this was again theory. Now you can see what are the techniques which are actually used in technical test analysis for each level. If we scratch debugging, which is not even testing, let's start with positive or verification testing. Of course, there needs to be enumerated the expected inputs, industry standards. For example, if you are testing banking software with XML, there is a standard called UNIFI, which defines how banks exchange data in XML format. So that's an industry standard. You can take the biggest and most ugly template of UNIFI XML, feed it to your software, and see if it crunches it successfully or not. But mostly this is just positive function. So if you have a database, you do select names beginning with A, you expect Andy and Amanda. But there is also proving negative function. This is not destructive testing, this is just negative function, like double negation, which means if you select A from names, you do not get Dave. And also checking error messages. For every error message there is in your code, there should be a test which proves A, that the error message only displays when there is the associated error, and B, it does not show in any other case. Do you have test cases for every error message you have in your software? So most companies nowadays, and I have visited several companies, even very large ones, focus only on verification testing, level 1, and from that only on subset of it, not even entire. So destructive testing, level 2, is what you should all aim for if you want to have decent quality and test coverage. And that includes a lot of techniques which we cannot go into now, but which we will touch later or on a separated course. Now, we have already said that testing does not equal quality control. Testing is just one of the activities, test execution. But even quality control doesn't equal quality assurance, which may come as a surprise in a field where everyone, without exception, call themselves quality assurance engineer. I haven't seen anyone calling themselves quality control engineers. Quality control is a reactive process. Imagine you have a factory. You are making, for example, shoes. So in a simplified view, let's say you have a conveyor belt, and on one end you put in raw materials, then you have some industrial robots, and they turn these raw materials into nice shoes. But you can also make some defective shoes, and you don't want those defective shoes to reach customers because they would say that your brand of shoes is low quality and they would stop buying them. So what do? You put quality control at the end of the assembly line. And the sole job of quality control is to figure out which shoes are defective and not allow them to be shipped to the customer, but instead throw them away on the pile of defective shoes. How does QC does that? Well, they must do some analysis to identify what could fail and hence what to measure on the shoes. For example, they should try to gently pry the shoe open if it will split because the glue is not sufficient. But the thing is, it's a reactive process. If you had 100% effective quality control and your robot was making 50% defective shoes, yes, there would be 0 defective shoes shipped to the customer, but you would still be losing 50% of all your resources and energy investments. So that's not very efficient, is it? So here is where quality assurance come into play. Because quality assurance tries to intervene across the product lifecycle to make sure the defects are not introduced into the product in the first place. And of course, quality assurance also includes quality control, because regardless how good your prevention is, you can never catch everything. So in our model example, how would the quality assurance look like? Well, they would invite a team of engineers from Toyota Automation, best class in the world, to fine-tune your industrial robots so they would stop making so many defective shoes. But isn't there anything else, anything better? Quality assurance also tries to change the design so that it's less prone to being defective. Ideally, quality assurance tries to make it so the design so that it's impossible to make the defects. So for example, they can engage with the product design team so that the shoe is designed in such a way that it cannot even split open because there is no tension which would cause the shoe to split, even if there was insufficient glue inside. Quality assurance is very much expert thing. It's heavy analysis. It focuses using some modeling techniques on identifying what could fail, how, and especially why. And then it does two things. It converts all this knowledge about what could fail and how into test cases, which vastly improve the quality control coverage, because suddenly the QC knows to look out for much more things than just if the shoe splits open. They, for example, can know that they should measure this particular part of the shoe because it's indicating of a poor quality. So that's quality assurance. In contrast with quality control targets just the build results. Do not release defective shoes or products to the customer, while quality assurance targets the entire design and architecture, and of course the build results as well. So quality control does not increase quality, it just prevents defects from being released, while quality control does increase quality. Quality control only analyzes to identify what to test, but quality assurance analyzes not only what to test, but also what to redesign and improve. And quality control is very much focused on the things which are visible at the outside, the things which are obvious, because that's what you test and that's what customers spot. While quality assurance is focused also on the things which are inside, like low probability, high impact faults, operations near the boundary limits, and things like that. And finally, quality control, it ends when the subject passes the test, because once the shoe is deemed okay by the QC and is shipped to the customer, for QC, that's the end of it. While for QA, because it's based on feedbacks and improving the design, there is no limit to how much you can improve the design. It's only how much time and resources you allow to that improvement. Now let's get practical. We have already seen the QC workflow. You do the technical test analysis, you design the tests, implement them, then you run them and evaluate the results. It's a streamlined process. QA is different by the feedbacks. You have the same research, analysis, design, implementation, testing, and evaluation phases, but you add the feedback. So in the analysis phase, you add some analytics heavy lifting, like fault hazard analysis, design envelope, modeling, and things like that. And these discover potential weak spots and risks. So these things, which are newly discovered by the QA analysis, are incorporated into design changes to the architecture or design or code, and also converted to test cases. And then it's fed back to analysis. Analysis is again done on these design changes to verify if they were enough and to verify if they do not create some new risks and problems. And so the design goes through several design analysis loops. And when the team as a whole or the product manager is happy, the implementation can begin. The important thing here is that it cannot be decision of just the QAs or just the developers, because QA would always want to have more sanitization, more error checking, more resilience and robustness, while developers would always want to just get on with coding already. So you start implementing, and there is one more thing, because regardless where you stop in the feedback design loops, there are always some risks which are left unsanitized, unmitigated. But you know about them. You just cannot fix them in the code because it will be too complex or too costly. But you can document these things you know about so that customers hopefully don't do them. Or if they do, you at least, your sustaining engineering at least has a knowledge base already prepared how to tackle that. And then there is one more and one final feedback loop. If a defect escapes into production environment and customer is unhappy, you do a escape defect root cause analysis. It's not blame game. Who's the bad guy who caused that? No, it's trying to find out what to improve so that next time this kind of defect would be safely contained, caught, and nullified before release. So the questions are two. First question, how did it escape the tests? Why didn't existing tests cover it? Was it such a fringe scenario that it's not sustainable to have tests for all these fringe things? Is it that we are missing some category? Is it that our automated testing has made some incorrect result evaluation? Is there something we can reasonably do to improve that? And why was it coded inside? Was it some program error? If so, can we introduce some coding standards to fix that? Or is it more reasonable to run a knowledge share session so that junior developers would, for example, learn some trickeries of the particular framework or language? So that's QA. It's about the feedback loops and design adjustments to improve before implementation. But it's also the focus on the lifecycle, because QC targets the defect-free release, and it does that through testing at the end of the finished product, while QA targets a quality product across its entire lifecycle, not only defect-free release, but also easy and nice installation, configuration, operation, good interoperability with other programs, because the customer may want to use the software in connection with other software from other vendors, and all of these pieces of software must talk together nicely. And also retirement and transition. And it does that through focusing on the design, although there is, of course, testing as well. So the question is, how do you start with proper quality control where you did not have any, when you had just some subconscious QC? The first and most important thing is to assign time and slots for the technical test analysis phase and test design. It doesn't matter how small that allocation is. The point is that you consciously go through these phases and you use some checklist or cheat sheet to verify that you haven't forgotten about any important test category or test considerations. So no more subconscious, but explicit and thoughtful. And also recognize that there is a difference between test implementation, execution, and results evaluation, because the length of these phases can differ very much, especially if you use automated testing, and you need to account for that in the planning. And finally, I said about the testing of the test, so using test classes checklist to verify that you didn't forget anything, but also you can introduce the QA method of doing root cause analysis if there is any escape defect. Why didn't the tests catch it? Now, I have mentioned test classes. What is that? When I was reading through the testing standards, I was reading one particularly boring standard, the IE 829, which is concerned with test documentation. And I found a buried treasure despite all the odds. They talked about designated grouping of test cases, summarizing their unique nature. And they put some examples like positive tests proving the function, negative tests proving that what should not have been on the output is not there, etc. And I suddenly realized that these things are pretty much a cheat sheet what to focus on when you are designing the tests. And that it also can serve as a checklist because there is finite number of these designated groupings of test cases with unique nature. So I did just that. I created test classes cheat sheet, which you can download on this website. And this is a checklist and cheat sheet which you go through when you are doing the test analysis. So it makes sure that you give consideration to every category of particular tests there are. You do not forget anything, and you don't have to create tests for each category. But if you do not create tests for some category, you need to be able to say why it's not relevant, or why the team decided not to bother with these. So that if a defect escapes and you do the root cause analysis, say you find out, wow, well, we didn't have any test cases for character conversion sanitization handling. Why is that? You can say, well, because the team thought it's not worthy. Well, obviously it was. So here we can see actually how this nicely maps to the test analysis levels. We have the positive testing, which is level 1, verification testing. We have the negative testing, which is the other and often neglected part of verification testing. We have the destructive and advanced testing, that's level 2, and equivalence classes and boundary values testing, which is inseparable part of any truthful testing. Inputs, output, front ends, compliance. Ever since GDPR, you have a legal requirement that if your software handles sensitive data which were encrypted, you cannot leave them unencrypted or you are facing heavy fines. So you should have some compliance tests for this. Try to crash your software and see if there are any unencrypted sensitive user data left. And things like that. So now we can finally get to the core, to the aerospace grade quality assurance. This is how it looks in real life. This is the official standard and the workflow from the official standard which you have to follow if you want to write software for commercial airplanes in the United States. You don't need to look into it, into the details. The thing is to do system thinking about it, to see how it really works. So the first thing is that it identifies the functions, all the functions the system needs to do. And then it identifies the ways in which these functions can fail and how bad it would be if they failed. And based on that, they can identify also with using some predefined list of environmental hazards, etc., what to do with it, if it's worth mitigating, if it's worth doing some sanitization, and implement it. As we talked, this is the design analysis loop we talked about in the QA workflow. And then test those things. So that's overview of the aerospace grade QA. But we will not use that because it has a lot of documentation, it uses some mathematics, it uses heavy auditing, and frankly, if no human lives or multi-million-dollar items are at risk from running and testing our software, this is probably an overkill. So what can we take from this for normal software development, for real aerospace grade QA with just the cherry picks and not the boring stuff? So the first step is the function list gathering. You take all the explicit functions, which are the requirements which the product owner or customer told you. And then you sit QA with developer and you go through these explicit functions and you identify also all the implicit functions, which means prerequisites for these. So to illustrate this, imagine your customer wants you to design an email service. And one of the explicit functions is that the administrator of the system needs to be able to add email users with their passwords. So the explicit function is to allow administrators to add users. And the implicit functions stemming from that are A, there needs to be a database of users where entries can be added. And that causes another implicit point, there needs to be a connection to the database. B, only administrators could have access to add new users. So that creates implicit function. Non-administrators cannot add users, and administrators can add users. C, the users must have passwords. So that creates implicit function that these passwords needs to be encrypted and using hash and salt. And another D implicit function, the salt used in the encryption of the user passwords must be unique for each user. So what is this good for? If the developer and QA started writing the code and the tests respectively based just on the explicit function list, somewhere in the middle of the development, they would encounter these problems. They would have to use their assumptions, and they would have to refactor everything they wrote so far to accommodate for these extra functions which are necessary, yet which were not foreseen. While if you identify all these implicit functions before you actually start coding, then you design from the clean sheet with everything you need. The second thing QA does is failure mode effect analysis. That's a QA technique, which means you take components, or in our case, functions, and for each function, you identify all the ways in which the function could fail, and what would it cause? How bad would it be? What would be the effects on the system? And that gives us two things. One, it gives us a very good idea about what is mission critical and what we need to sanitize. So after doing the failure mode effect analysis, the QA can tell the developer what are the additional risks discovered, which need some extra sanitizations in the code. And second, each failure mode, which means the way in which something fails, is de facto a test case. Because if there are multiple ways in which a component could fail, you just go and you write test case for each of these, and you verify that if such conditions happen, the result is not a disaster. If some of the effects would be particularly dangerous, like loss of a human life, or in our case, loss or unlimited distribution of customer data, that would be deemed a critical function. So you do some advanced analytics on it, but only for the critical ones. And then we do the classical technical test analysis using test classes, and that will fill us more important test cases and considerations. And then it's just the matter of implementation, execution, results evaluation as always. Now, that may have left your head scratching. I told you that QA is about feedback loops and about focus on the entire life cycle, and that it's interdisciplinary and developers and QAs work hand to hand in that. So where is all this in this flow? Nowhere, it's here. This is the same flow, but displaying also the feedbacks and the multidiscipline teams. So we start here with the function list. We identify the explicit and implicit functions. And when we have that, we have the function list. And what do we do with that? The developer takes it and converts it to unit tests, which he uses to write his code. Voila, test-driven development. The QA takes the function list and copies them into the test case suite, because every function, explicit or implicit, is basic functionality which needs to be done by software. So that's basic positive or negative test. And then QA goes and does the failure mode effect analysis on all the functions. And by doing so, QA finds all the ways and the reasons why the software and the functions could fail. So these give us pretty good idea about the advanced and destructive tests which are needed. Then we take the test classes and use them as the cheat sheet to fill in all the blanks and consideration about the systems, compliance, and everything else. And by doing so, we have gathered additional data, which allow the developer and QA to talk about design mitigations, which would prevent these failures from occurring. And for each things which are sanitized in the code, based on that feedback, we also add a new test to verify that the sanitization did indeed work and catch all the possible risks. So all these things together, including the optional fault-free analysis, are reflected in refining the code so it's as bulletproof as possible. And from the code, there also stem the equivalence boundaries and partitions, because the developer selects the limits, like the allowed length of a field or variables during coding. So they must give that feedback to QA, so these are also incorporated in the tests to be verified. So this altogether gave us extremely good coverage of tests. Using all these analytical techniques, we can really trust our tests to cover almost everything important. It increases the confidence in the product. So with this test design, we can just implement it, that converts it to executable tests, and then we test it. If the tests have not passed, we refine them, and the refinements are again tested until it passes. And when it passes, great, but it's not ending there. There is the last feedback loop if a defect is found. So if a defect is found, the developer and QA do together the defect escape root cause analysis, find out why was it not contained, and again, code is refined, tests are added, and it's everything combined, and the fix is released. So this is aerospace grade QA. Of course, you can just start with the function list and very simple improvised failure mode effect analysis done on a paper with a pencil, and it will increase your QA already. But if you want to get better, we are actually offering in Broadcom a free course on very advanced test analysis techniques, which includes all these things. So you can just ask Zuzka Pruchova when it will be open and get in the list. So we are at the end. I want to encourage you that this is not some theory. We have been there and we have done that. When we in my team adopted the formal test analysis technique, the number of test cases covering new features increased in average twofold. When we adopted test classes as the cheat sheet and checklist, the number of test cases and coverage increased further twofold, and it gave us increased confidence because now we were certain that we didn't skip anything important or forget anything important. When we were given opportunity by quality product increment, which meant 3 months which we could dedicate to quality, we were able to do root cause analysis of all the historical customer defects and join that with fault tree analysis straight from NASA handbook on fault tree analysis with aerospace applications. And that has done two very interesting things. One, it gave us unforeseen and unprecedented understanding of how this legacy feature, which was 10 years old, actually works. And many of the things which I discovered while doing the fault tree analysis surprised even the most senior developers on the team and even the team architect. And it also helped us find the problematic portions and fix them. So the feature on which we did this stopped being the problem feature. And finally, when we introduced the function lists and failure mode effect analysis, that didn't increase the number of test cases almost at all, but it did stop several weak implementations before they were implemented. I identified all these things before the developers actually started properly coding. So we just sit as a team, we talked about them, we decided what is worth mitigating and what not, and we changed the architecture profoundly, and the result was much more robust and resilient product which was with very cheap changes. Nothing had to be refactored. We just changed the design before it was implemented. And we did all that with just 2 full-time QAs in the team. So it can be done and you can do it too. Last slide. Testing as the activity of executing some test scripts is just the tip of the iceberg. If testing is defining a running test which someone else designed, anyone can do that. But the important things happen before the testing. It's the test analysis and design. That's where all the quality comes from. So whoever does also technical test analysis is not a mere tester, but test analyst, or if he does all, a QC engineer. So that's a growth path, a career growth path, which is unfortunately overlooked, but it's extremely important. And if someone does fault hazard analysis and failure mode effect analysis and design reviews, that makes the person a QA engineer. Automation cannot replace analysis or analyze risk or define testing data. It's not its job. It cannot be mispurposed to do all these things. You can try to mispurpose test automation to magically do that, but it cannot do it and it will fail you. Test automation can just allow you to test faster, run the test faster, and more often. But if you focus on test automation too much, which is an unfortunate trend almost everywhere, it will redirect the focus on execution phase from analysis phase, and the quality of the tests and of the product will drop. That's why we are seeing so many incredible defects, even in software from major companies as compared to like 5 years ago. All the focus is on execution and automation, and people don't care about analysis too much anymore. Code coverage is misleading metric because it's useless compared to path coverage, and even then, it doesn't cover the data, which are the crucial part about quality assurance. And level 1 testing, just positive testing, is absolutely dangerously insufficient, although most companies do just that. And you should aim for destructive testing as the minimum, while the real quality starts with preventive QA on level 3. So thank you for your attention. I know it was a long and information-packed session. And if you have any questions or complaints, now it's the time to go.
I don't see any questions, and since we are pretty far over time, I think maybe we should just wrap up. If there are any questions, please feel free to add them to the post session survey, and we'll get back to you as soon as we can. Thank you very much for your time today, and have a great day, everybody.
Bye.